So good evening to one and all. Is the voice and video clear to everyone? Say thank you. So let us start our today's session. So before going to start the topic of sequences, so can you recollect what we have done on sequences in the previous class of real analysis? We have given one formal definition of limit. Later, based on the definition of limit, we have solved some problems. Then we have taken the concept of monotone sequence, as well as what are meant by bounds and types of sequences. This thing we have discussed earlier. I hope this is our previous session with regard to real analysis, right? So do you have any conceptual doubts with regard to those topics? To anyone? So is everyone clear with those things? Okay. So in today's session, initially I want to give some properties of the concept of limits. Then I want to give some standard results. Here standard results are nothing but the theorems. Those proofs are not at all required for everyone. Generally proofs will not be given to you, only problems will be given to you. So if you talk of discussing proofs, that is totally a different issue. It takes a lot of time. So you can check for previous year questions that there is no proof given at all. And then I want to take some problems on monotone sequence. And based on results, I want to say some more problems and the problem solving strategies. So that I wish to take for today's session. So initially we go with the basic level and medium level problems. Then in the upcoming session, we think with the advanced ones, which means the level of the UPSC. Fine. So this I wish to plan for today's session. Any other queries to anyone? Okay. So can we begin this session? Right. The first one is suppose I have a sequence Fn which has a limit L. The first result is if you say that the sequence has limit, it is convergent. And every convergent sequence is always bounded. So you are able to define what is the least upper bound as well as greatest lower bound for the sequence. Okay. So this is one result we need to understand. So please take a note of that. Then if you talk of the opposite, it is need not true. Because if you take a bounded sequence, you cannot say that it is always convergent. The simple example is, which you have seen earlier, -1 whole power n, the sequence. So if you write the terms of sequence, it will come as -1 1 -1 1 and so on. So you can say that the sequence is oscillatory. You cannot say that it is tending to a fixed value, but we can say that it is a bounded sequence because it has the least upper bound -1, sorry, greatest lower bound -1 and least upper bound 1. Okay, is that clear? Fine. One other property is the limit of the sequences will satisfy the algebraic properties. What it is? Say you have two sequences, Fn and Gn, and both are convergent. So what happens? Let us say Fn has limit L1 and Gn has limit L2. The algebraic property is nothing but applying the algebraic operations. So you can perform addition, subtraction, division and multiplication over the sequences. So if you obtain the new sequence Fn plus Gn, then it will be converged to the limits L1 plus L2. Is this fine? The algebraic property? Right. So in the same way, you define for the negative also. We can say that Fn minus Gn will tend to L1 minus L2. That is one property. So you can consider the product also. So if you define the product Fn into Gn, it will tend to the product L1 into L2. Now, if you talk of the division, say Fn by Gn, so since the denominator should not be undefined, so limit L2 must be not equal to 0. So it will tend to the limit L1 by L2 where L2 is not equal to 0. Okay. So please take a note of these properties. If you head it out, you can ask. For every property there is a proof, but proof is not required. If you are more interested in the proof, I will give the proof as a file in the Telegram group, you can check. Right. One other property is, since Fn converges to L, multiply the given sequence with a number. So you have a new sequence C into Fn, it will converge to C into L. That is one property. The other one is, consider the reciprocal sequence 1 by Fn, it will tend to 1 by L where L is not equal to 0. This is one more property where the limit is not equal to 0. And one interesting property is, say I have two sequences Sn and Tn. In the two sequences, one is convergent, the other one is a bounded sequence. And I am saying that the sequence is converging to 0. It tends to the value 0. So if you consider the product sequence, it will tend to 0. So this is one important result we will make use of occasionally. So you take a note of that. So another one is if limit Sn equal to 0, then limit mod Sn is also equals to 0. It tends to the same value. So are they noted? Fine. So can I erase this? Okay. So one strategy is, if you have a sequence Sn, so if you want to prove that Sn converges to a value L, then from the sequence you will get the two subsequences S2n, S2n minus 1. Nothing but all the even terms in the sequence and all the odd terms in the sequence. So these are nothing but the subsequences of Sn. If both these values has the limit L, then we say that the given sequence has the limit L. So that is one result. Another important one is, we have sandwich theorem, or we call it as squeeze theorem. So it is just like, if you imagine the sandwich, so let us take three sequences Sn, Un and Tn. I think you come across with this result, the sandwich theorem, earlier at the level of calculus. I hope so. As and when you take three sequences, you have the property that Sn less than or equal to Un less than or equal to Tn for some n greater than or equal to k. That means if you observe the terms of the sequence, from a particular term onwards, all these sequences are maintaining this type of order. And if you are able to prove that the lower sequence and upper sequence both converge to the same limit, then automatically the middle sequence also tends to the same limit. That is the case of sandwich theorem. So what it states, as and when you have three sequences like this type, Sn less than or equal to Un less than or equal to Tn, and if you are able to prove that the lower sequence and upper sequence are tending to the same limit L, then the middle sequence also will tend to the same limit L. Okay? Is the concept clear? So as and when a problem is given to you, it is your own specification that you are able to build two more sequences from that. So the first sequence is less than or equal to given sequence, it is less than or equal to another sequence. And you should be able to prove that these two values are belong to the same limit L. So we will do it by means of construction that we will do later while doing the problems. So then the another important result is, based on this result we will prove so many problems. Monotone theorem or monotone convergence theorem, you can call it all. So you take a sequence Fn which is a monotone sequence. It means that Fn is either increasing sequence or decreasing sequence, whatever the case may be. And if you say that the sequence is monotone and the sequence is bounded, then it becomes convergent. So the only thing you need to do is, as and when a sequence is given to you, you should be able to say that it is monotone. So you have to verify it is either increasing or decreasing, and you should be able to specify it is bounded. So you need to tell this is the lower bound and this is the upper bound. Then automatically by this theorem, it becomes convergent. That is the concept of the theorem. So in other words, if you take an increasing sequence, it always tends to the least upper bound. The limit is nothing but its least upper bound by the concept of this theorem. Another one is, if you take a decreasing sequence, it always tends to its greatest lower bound. The limit is nothing but greatest lower bound. So you please take a note of these points. So I think since I have given a lot of results, so let us take some more sample problems. Then we have a clear idea about this concept, right? So I want to take some more problems on monotone theorem, which gives the idea. Right. So can I proceed further? So may I know that how many of you have prior knowledge over this topic or any preparation or not yet? So one person has a prior preparation. So what about the rest? So that I will plan accordingly my sessions. Yeah. So if you have done this concept at the level of engineering, to what extent you have studied, can you tell with regard to sequences? The outline, the last one which you have studied, the chapter you can say. Can you give a guess on that? Okay, thank you. So up to Riemann integration, fine. So you have done 50% of the total syllabi in such a case. So let us take one problem that I have given the sequence Sn and it is defined as Sn is equal to 3n plus 4 by 2n plus 1. Now your wish is you are going to prove that the sequence is convergent. So this is sorry, this is the problem. I have given the sequence Sn where the nth term is defined like that and you have to prove that it is convergent. Okay. Now let us use the technique of the monotone convergence theorem. So this is the problem. You have to verify that the sequence is convergent. So I have to verify whether it is increasing or decreasing. So what I am going to use, I am using the technique of monotone convergence theorem. So if you say that the sequence is increasing, so it is of the form first term less than or equal to, second term less than or equal to, so on. So if such is the case, Sn less than or equal to Sn plus 1 is the property satisfied by the terms in the sequence. Accepted? Right. So if you want to prove that the sequence is increasing, so you can calculate the difference between the two terms. So you can find either Sn minus Sn plus 1 or Sn plus 1 minus Sn. So if the sequence is increasing, if you consider the difference between these two terms, it must be positive, right? Yes or no? So by using this technique, since the nth term is given, I will write the n plus 1 term. I will calculate the difference between these two and I say that it is positive so that it becomes the increasing sequence. Fine, the objective of the problem. You can do the same thing for decreasing also. If it is decreasing, S1 greater than or equal to, S2 greater than or equal to, so on. So what happens? You have Sn greater than or equal to Sn plus 1. In this case, you need to consider difference between Sn minus Sn plus 1. It will be positive, so that the sequence is decreasing. Right. Now, to represent on paper, first we will write Sn is equal to the value 3n plus 4 by 2n plus 1, and Sn plus 1 is nothing but substitute n plus 1 in place of n. So I think that it will be the value 3n plus 7 by, so 2n plus 3. Am I correct? Finding Sn plus 1, right? Now let us consider the difference between these two. You can take either of the difference, that is up to your choice. So simply find the LCM and tell me the value. I say that it will be 2n plus 1 into 2n plus 3 in the denominator, and what could be the numerator? Just find the LCM there. 5. As and when you define a sequence, we start that n belongs to the natural numbers in defining a sequence. So here n is a positive number, so denominator is positive, and you have obtained that 5 is a positive value. So this whole thing is positive. Accepted? Any questions to anyone? Yes or no? Are you getting the idea what I am saying? Right. Sorry. So here you say that Sn is greater than Sn plus 1. So it is a decreasing sequence. Accepted? Right. So to prove that it is convergent, the path left with us is, you should say that it is bounded. Since it is decreasing, always it must have the maximum value. The first term would be the maximum always, isn't it? So to say that it is bounded, I should know what is the lower bound of this sequence. In other words, you should be able to specify that every term in the sequence must be less than something, so that you have identified this is the lower bound for this sequence. One lower bound is enough. Now, how to find it? Can I proceed now? Okay. So again, take the same term, Sn is equal to 3n plus 4 by 2n plus 1. Since the denominator is 2n plus 1, using that I am writing numerator somewhat different. So how I am writing? You simply divide 3n plus 4 with 2n plus 1. How it comes? 3 by 2 here. It will be 3n plus something. If you subtract, what could be the value here? It gets cancelled. 5 by 2, right? So how I am writing that? So this is the divisor, dividend, quotient and remainder. So I can write that 3n plus 4 is equal to 3 by 2 into 2n plus 1 plus 5 by 2. Accepted? The division algorithm, right? So this is equal to, in the numerator I am going to write it as 3 by 2 into 2n plus 1 plus 5 by 2 whole by 2n plus 1. This will be 3 by 2 plus 5 by 2 into 2n plus 1. Now what happens? The nth term formula I have modified like this. It gives what? If I want to write the sequence by putting n is equal to 1, 2, 3, so on in this, I can write the whole sequence, right? Yes or no? Are you getting? Fine. So if I put n is equal to 1, I will get S1. If I put n is equal to 2, I will get S2. So what happens? Whatever the term you find in this sequence, it must be nothing but 3 by 2 plus something. Accepted? Because I have written the term like this. So I can say that 3 by 2 is less than Sn for all n. That's it. You have found the lower bound here. Therefore, I can say that the sequence is bounded. So earlier I have considered the difference and I proved that it is a decreasing sequence. Now by modifying the nth term, I have proved that it has the lower bound 3 by 2. So the sequence becomes bounded. Therefore, by monotone convergence theorem, the sequence is convergent. That is the conclusion. So here we are not finding the limit of the sequence and we are simply checking the nature of convergence. Whether limit exists or not, that is what we are actually doing here. Okay? Is the concept clear? Right. So this is the first problem. So as and when the nth term is given very specifically, you can do this type of modification and you can prove that. So let us go for the other one in the similar pattern. Shall I go? Right. The other question is, if I have defined Sn is equal to 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus so on plus 1 by n into n plus 1. You need to verify the sequence is convergent. This is my second problem. So please take a note of that. Is this clear? So in the same way, let us find the next term, that is Sn plus 1 here. It is equals to 1 by 1 into 2 plus 1 by 2 into 3 plus so on plus 1 by n into n plus 1 plus 1 by n plus 1 into n plus 2. Now you simply consider the difference between these two. In either of the way, you can consider the difference, Sn plus 1 minus Sn or Sn minus Sn plus 1. Both are acceptable. So the value is nothing but 1 by n plus 1 into n plus 2. And it is positive. Accepted? Yeah. So from this, what we can say? Is it increasing or decreasing? Yeah, it is an increasing sequence. Everyone agrees with this. Any queries for anybody? Any queries? Yes or no? Fine. It is an increasing sequence. Now, for an increasing sequence, the lower bound is nothing but the first term. Decreasing, let us say, this is greater than 0. It means that means it is increasing. Accepted? From the difference it is considered. Fine. So since it is increasing sequence, so we have to say that the lower bound will exist by default. We need to find the upper bound. So how to find the upper bound? By rearranging the terms in Sn, we can find the upper bound. That is one strategy. So you have Sn is equal to now, can I write this value as is this acceptable to write? So if you observe that the terms gets cancelled, the first and the last will remain. So if you consider the LCM, it is nothing but n by n plus 1. It is always less than 1. Because if you divide a number by one increment, then automatically the value will be less than 1. 5 by 6, 2 by 3, 3 by 4, always the value is less than 1. So what is the upper bound of this sequence? 1. Therefore, it is bounded. Therefore, by monotone convergence theorem, it is convergent. Okay? Is this problem clear for everyone? Any questions, please? If so, please ask. So please take a note of this, then I go to the next problem. Sorry. Fine. So the next problem in the same pattern, I am going to take it as this is my problem. I just want to add something here. This I want to write actually. One plus 1 by 1 factorial plus 1 by 2 factorial plus so on plus 1 by n factorial. And the objective is I want to show that the sequence is convergent. So as usual, you take Sn plus 1 here, nothing but 1 plus 1 by 1 factorial plus 1 by 2 factorial plus so on plus 1 by n factorial plus 1 by n plus 1 factorial. So if you consider difference, if you consider Sn plus 1 minus Sn, this value minus this value, it contains one term extra. It will be 1 by n plus 1 factorial. So the value is greater than 0. Accepted? Yeah. You are asking about the theorem. On what theorem I am going to solve the problem, right? Yeah. Here the thing is, we are using the technique of monotone convergence theorem. The theorem states that whenever a sequence is given to you, you should prove first it is a monotone sequence. That is, you must specify whether it is increasing or decreasing. That is step 1. Step 2, you must say it is bounded. It has the lower value and the highest value. Then As a result of the theorem, it becomes convergent. Here we are not evaluating the limit, we are saying its nature. It will get a limit, that's all. Fine. Okay. Right. So at this point, what we can say? It is an increasing sequence. Accepted to all. Now, how to find its lower bound? It is the issue here. So again, take Sn. So if you write the exact values there, is this correct? The expression value? Now, I want to say Sn is less than something. This is my task actually. So I should go with my own arrangement so that using this relation, I am going to specify Sn is less than or equal to something. So here I want to say that this will be 1 plus 1 by 1 plus 1 by 2 plus 1 by. Can I write like this? Please observe. This is my intention here, what I am writing there. So I will write like this. 1 plus 1 by 2 plus 2 into 2, triple 2, 4 2's, up to n minus 1 2's. Any queries? Why I have written only 2? You can take 3 also, right? Will you agree? So here, by checking the number of terms here, I am taking that much number of 2's, one short of it. So if I take, it is nothing but just 1 by 2. So 1 by 2 less than or equal to 1 by 2. This and this. So if you take 1 into 2 into 3, so by taking the reciprocal, you can take 2 into 2, 1 by 6 less than or equal to 1 by 4. As in when the number increases, I am fixing only 2 in the denominator. That's it. You can fix 3 also. You can write it as 1 plus 1 by 3, 1 by 3 into 3, 1 by 3 into 3 into 3, 1 by 3 into 3 into 3 into 3 like that. That is also you can do. Okay. You can do any kind of rearrangement there. All I want to do is nothing but Sn must be less than some number. You should be able to prove that. Suppose if you have a little doubt, then start taking the terms of the sequence. Write S1, S2, S3 and check whether it is follows or not. Okay. Is it acceptable? Fine. So here it is nothing but 1 plus, if you take 1 by 2 as common here, so on, the last value will be 1 by 2 power n minus 1, like that. Or with that you can simply say like that. Or you can remove this thing also. 1 plus something. All I want to trying is nothing but Sn must be less than something value. That's all. You can do any kind of modification in this arrangement of terms. That's up to your choice. I am simply writing that 1 plus 1 by 2 plus 1 by 2 square plus 1 plus 1 by 2 power n minus 1. So it is in the form of arithmetic progression, sorry, geometric progression. So if you have the sum of the n terms, you can write the formula Is this correct? The formula? Sum of the n terms? Okay. So here r is nothing but 1 by 2. So applying this value, you will get that can you say the value would be? On doing the simplification. So let me know how many of you have the doubt at this step. Right. So the objective here is after rearrangement. Okay. So with that a simple clarification, let us do like this. If you take S1 from the definition of the sequence, what it will be? 2. What will be S2 from the part? You should give that the form of the expression which is given there. So you can say that 2 plus 1 by 2 factorial. Is that correct? So if you write S3, 2 plus 1 by 2 factorial plus 1 by 3 factorial. So every time I am writing that, if you compare each and every term, so I am representing everything as this is less than or equal to how many times of 2. That is my whole intention. Not only take 2, you can take 3 also. Since it is earlier given 2, I am representing in terms of 2. That is the ideology. So if you compare the terms here, just do that. So this is 1, this is already 1, then you have it is 1 by 2. Here at this position, it is nothing but 2 into 3. I can write it as less than or equal to 2 into 2 here, for 1 into 2 into 3. This part and this part when comparing. So in this term, if you take the value here, it will be 1 into 2 into 3 into 4, the 4 factorial. So there I will write 2 into 2 into 2, because this one is negligible here. You have 3 numbers, 3 2's. Okay, right. So on, if you go with the last one, here neglecting this one, you have n minus 1 digits here. So 1 by 2 into so on 2, n minus 1 times it will come. So by taking the values here, you can take 2 as common, and the rest of the thing is nothing but in the geometric progression. Accepted? Say Fine. So on simplifying that, you will have a finite value. In a short manner, since you know the simplification part, I simply write that it will come as, I think, 3 minus 1 by 2 per n minus 1. I hope so it will come like this. The value 3 minus 1 by 2 per n minus 1 on simplifying the geometry progression sum, the formula I have mentioned earlier. So just understand that our task is nothing but having an upper bound. You can do the arrangement not only in terms of 2, you can do the arrangement in terms of 3 also. That is also acceptable, not wrong at all. So at this part, what happens? This whole value is nothing but 3 minus something. So what happens? Sn is less than 3. So the upper bound is nothing but 3. That was the concept. So earlier you have proved it is increasing. Now you proved it has the upper bound. I have written the final answer on simplification. Right. Maybe you may have the other number, but at the end you just have a number, right? Sn is less than some number. Are you able to specify or not? In the examination point of view, there is no need to simplify that expression also. You can simply mean that it is a finite value. You can just write like that. That is also acceptable. The concept is not finding a number. The concept is finding that it has an upper bound. That's it. That is the whole idea. So apart from traditional maths, it is somewhat different. Please understand. We are not particular about the value. We are particular about the concept, whether it implies here or not. Okay. So you have proved it has an upper bound, hence it is convergent. The problem completes. Please understand one more thing, that I am not finding what is the limit of this sequence also here. I am just finding it is convergent. That's all. Okay. Fine. Now let me take an interesting problem. So you can expect the concept of UPSC levels from this level onwards. I am getting a little middle one. Okay. Please understand, I am saying 3 minus something. Three is the upper bound. How can you say that least upper bound without knowing this value? Isn't it? You can fix 3 as an upper bound. So obviously here you can say that it is the least upper bound. The least upper bound is nothing but 3 minus this. This is the least upper bound. If you exclusively consider 3, it is the upper bound. I think you feel the difference. Because 3 minus this thing is a number. Accepted? Okay. Yeah. So Sn is less than some number here, and this number is less than 3. So 3 is the upper bound. This would be the least upper bound. So if you find a limit, Sn converges to this number, not to this. Fine. Okay. So please understand, initially the first 1 or 2 chapters looks like a dry subject. Later on you try to improve yourself because you are learning for the first time, because you didn't come across this type of methodology earlier. I hope so. Okay. The one disadvantage of this real analysis concept is, you know the concept well, you know how to apply the concept. As and when a problem is given to you, which concept you need to apply here is a question mark. You are well versed with each and every concept, every formula, how to do. But the thing is, what is the specific formula I need to use at this point? That is the only doubt. For some chapters, you are very easy to apply the formula and solve. For some chapter, it is little difficult. That's it. Except this, the subject looks good. Right? So let me take the other problem. I have the sequence Sn, which is defined by the first term is 1. From second term onwards, it is defined by the recursive formula an plus 1 is equal to 2an plus 3 by 4 for all n greater than or equal to 1. And you have to verify that the sequence is convergent. Okay. Please take a note of this. After noting, please inform. So if everyone feels difficulty in this concept as and when you please inform, I will elaborate the step one more time. Don't hesitate to ask. So is this problem clear? The sequence is defined by means of a recurrence formula, recursive formula, what you call it. So whenever the sequence is defined by means of a formula like this, we always use the technique of induction. You should remember this concept. For most of the problems, if the sequence is defined by means of a recursive formula like this, whatever the formula may be, we use induction for applying the monotone convergence theorem. So, for applying monotone convergence theorem, you have two parts. You need to say it is monotone, and you need to say it is bounded. So in each cases, you are applying induction. To proving monotoneness, you are applying induction. In proving boundedness, you are applying induction. Okay? Is the perspective of the problem clear? The strategy? Right. So, first of all, let me write the sequence values, the terms in the sequence first. So on paper, first we write this is the sequence and the terms are defined like this. So if you list out all the values in the sequence, it is going to come as a1 is equal to 1, a2 is nothing but a1 plus 1 from this point. So 2a1 plus 3 by 4. Seven by 4. Accepted? Sorry, 5 by 4. Accepted? Fine. So if you go for A3, it is A2 plus 1. So give me the value there. By 8. So in this way, all the terms we can list out, right? So my first part is I want to prove its monotoneness by means of induction. So you take the first term and second term, check which one is big, which one is small. A1 is less than A2. Accepted? All of you agree? Yeah. So we have, so for n is equal to 1, sequence increasing, I am applying the mathematical induction. So you assume for n is equal to k, that is ak is less than ak plus 1. Accepted? I have assumed the induction step. Now I have to prove the result is true for k plus 1. It means that I have to prove that ak plus 1 is less than ak plus 2. This is my objective. I need to show this. How I am going to show this is using this induction hypothesis and observing this recursive formula. I will prove my task. How it is going to be? If you observe the terms in the numerator 2an plus 3. So first of all, you multiply both sides with 2. Then add 3. Then divided by 4. So as per the recursive formula concerned, this is ak plus 1 and this is ak plus 2, and you have obtained that ak plus 1 is less than ak plus 2. Okay? Is that clear? Any queries? Okay. Now I have to prove that the sequence is bounded. Since it is increasing, the least value is nothing but 1. Everyone knows that. I need to show what would be the upper bound of it. So I will say a1 is equal to 1. This is less than something. As and when you specify something here, this must be the upper bound for each and every term of the sequence, because you are using the induction technique here. We should be very careful. So if you observe, this is 5 by 4, around 1 point something, 11 by 8, around 1 point something. So everyone is coming as 1 point something, right? So can we take that 2 is upper bound of the sequence? It is a guess, isn't it? You can take 3 also. You can say that 3 is an upper bound. So how I am fixing the upper bound here? Roughly observing first 1 or 3, 4 terms of the sequence, I am guessing that this could be the upper bound and using that technique in the process of induction. Is the strategy clear for everyone? Fine. So I say that since these are nearly tending 1 point something, 1 point something, I am feeling that 2 will be the upper bound. So I say that a1 is equal to 1, this is less than 2. So this is induction step for n is equal to 1. We have proved that 2 is the upper bound. Assume for n is equal to k. So what is that? Induction step is nothing but ak is less than 2. Now I have to prove ak plus 1. So I have to show that ak plus 1 is less than 2. How I am going to show? Again using the same recursive formula. So since ak is less than 2, multiplying with both sides with 2, 2ak is less than 4, adding 3, 2ak plus 3 is less than 7, dividing with 4, 2ak plus 3 by 4 is less than 7 by 4, and this will be less than 2. Say, everyone is getting the strategy, how I am applying the induction? Any queries you can ask. So that term is nothing but ak plus 1. So I have proved that ak plus 1 is also less than 2. So by mathematical induction, 2 is the upper bound, hence the sequence is bounded. Therefore, by monotone convergence theorem, it is a convergent sequence. That is the conclusion. Okay? Are you getting the concept? Yeah. So I want to take one more problem on this model. Can I? So if you have noted this, you please inform. Everyone? Fine. Now, this is the problem. I think it is given in the previous papers. I hope so. The similar model. I have the sequence Sn defined by first term equal to root C, where C is greater than 0. And from second term onwards, it is defined as root of C plus Sn for all n greater than or equal to 1. And you have to prove that it converges to the positive root of this was the question. The sequence converges to the positive root of x square minus x minus c equal to 0. So after noting it, you please inform. Fine. So again, the procedure is clear. I am using the technique of induction for proving the monotoneness as well as the boundedness. Now, how to prove this? Let us go with the monotoneness, that we have S1 is equal to root C and S2 is equal to root of C plus root C. Accepted? Yeah. So my concept is I have to show S1 is less than S2. How? Right. The thing is, simply observe the terms in the square root. So we can say that C is less than C plus root C. Accepted or not? By simply observing the term values, I am saying that. So applying root on both sides, root C is less than root of C plus root C. Hence, S1 is less than S2. So for n is equal to 1, the sequence is increasing. It is only construction part. How good you are at your logic in getting a construction means you have solved the problem. That is the idea behind this. Okay. Is this step clear for everyone? Right. Now, having the induction hypothesis, you assume for n is equal to k, that is sk is less than sk plus 1. I have to prove for k plus 1. How I am going to prove? Take the same recursive formula. How it is applied? The constant c is added and you have the root here. So taking that, c plus sk is less than c plus sk plus 1. Applying the square root, root of c plus sk is less than root of c plus sk plus 1, which gives that sk plus 1 is less than sk plus 2. If you clearly observe the pattern of the recursive formula, you can apply induction very easily. So by mathematical induction, we say that the sequence is increasing. Okay. Are you getting? Yeah. Now I have to show that it is bounded. How to show that I am bounded? Let me say I have taken the first value. Now I need to say that every value in the sequence must be less than something. How this something I should get as a guess in my mind? One basic strategy is always root of a number is less than the number, isn't it? If I say root 2, it is less than 2. Accepted? So can I say that if S1 is root C, can I say that this is less than C? Yeah. Now the question is, in the problem, there is no mention of the criteria of C. Because if you want to say that C is upper bound using induction technique, each and every term of the sequence must be less than C. You should be able to prove. So if C is equal to 1, what happens? Is that criteria correct? The strategy? He simply mentioned that C is a number, a positive number he mentioned. You don't know whether C is 1, 2, 3, 4, 5 or 1.5, you don't know at all. So if C is 1, will it works? No. So what happens, since I don't know C, this is always holds for C is equal to 2, 3, 4, so on. For 1 it fails, so I say that it must be obviously less than 1. Accepted that? Even though C is 1, that will be accepted, right? Yeah. So in selecting the upper bound, I am using this logic. Always root x is less than x. If x is equal to 1, that won't accept. So I have taken that C plus 1 could be the upper bound. So by assuming the upper bound like this, I am proceeding the thing. Okay. So does it make sense for everyone? Yeah. So for n is equal to 1, C plus 1 is the upper bound. I am applying the induction technique. So assume for n is equal to k, it means that you have said that Ck is less than C plus 1. Induction hypothesis. Now applying the same recursive formula, you have to prove Sk plus 1 is less than the same C plus 1. So apply the formula, add C on both sides. So C plus Sk is less than 2C plus 1. Since root is there, apply root of C plus Sk. This is less than root of 2C plus 1. So you have get that Sk plus 1 is less than 2C plus 1. Now how I am going to get that this is less than C plus 1? Here I have a problem, isn't it? I think everyone is getting the strategy. Any doubts for anybody so far in the discussion? Yeah. Now, since I know that this is less than this value, if I add something to this, then also the something value also is the upper bound of this. So I say that this is less than 2c plus 1 plus c square. Accepted? Why I have taken c square? Because my aim is to prove that c plus 1 would be the upper bound. That's why I have added c square in the root. So it is nothing but c plus 1 whole square. This is equal to c plus 1. So this is the ideology. Sometimes while applying the recursive formula straight away, you will get the answer. So as and when applying the recursive formula, if you have stuck it at some point, then since my objective is this, what I can do in the modification while getting some arrangement here. So our task is nothing but proving the upper bound is c plus 1. That's all. Okay. So sk plus 1 is less than c plus 1. So by induction, it has the upper bound. Hence it is bounded. So it is a convergent sequence. Okay. Any queries for anybody so far? If the part is clear, I will go with the remaining part of the problem. And you can mention if it is boring. Fine. So can I erase this part? I can make space here. So as per the problem concept is concerned, the task of the problem, we have proved by applying monotonic convergence theorem, it is a convergent sequence. The other part left is we have to prove that the limit of the sequence is satisfying this equation. It converges to the positive root of x square minus x minus c equal to 0. This was the question tag there. It means that if you evaluate the limit, say the limit is L, L is going to satisfy this equation. That was the concept. Okay. Since it is a quadratic equation, it will have two roots. And obviously, on observing this, you can say that one root is positive, one root is negative. Since if you observe the pattern of the sequence, each and every term of the sequence is positive. So what happens, if you calculate the limit, it is also positive by default. So there is no need to specify that the limit of the sequence is positive, because every term in the sequence is positive. If we evaluate its limit, it is nothing but positive. So my task is nothing but I have to say that the limit of the sequence will be the root of this equation. In other words, the limit satisfies this equation. That is the thing left with me. So let us assume that limit n tends to infinity, Sn is equal to L. It means that the sequence has limit L. So what happens from this, I can say that limit n tends to infinity, Sn plus 1 is also L. Is this right? Please tell. Accepted or not accepted? Yeah. As we have studied the algebraic properties of the limits earlier, so at this point of view, I say that okay, sum of the sequences, division of sequences, product of sequences, I have given the algebraic properties of limits earlier in the beginning of the session. So if this sequence has limit L, if you consider the square of the sequence, the limit is nothing but L square. Okay? Fine. As per the product of the sequences considered. Yes or no? Yeah. So you know that Sn plus 1, if you take a square, it is nothing but C plus Sn is equal to L square. So apply limit to this part, it is a constant. So C, if you apply limit n tends to infinity Sn, it is nothing but L is equal to L square, implies L square minus L minus C is equal to 0. So it gives that L is the root of the equation this. In other words, L satisfies the equation. That's it. Okay. So in this way we have completed the problem. Any questions please to anyone? So you please take a note of this. Then in the similar pattern, I will give a problem to you just for a practice. You can take it as an assignment, I can call. So using the same induction technique. So after the completion of sequences, I will give a list of problems for you as an assignment, or for the completion of 1 or 2 topics, I will give it, because I want to concentrate on the fundamentals and the strategy of techniques. Later you are able to crack any kind of assignment, because I hope that everyone is following some kind of standard textbook. If you know the strategy, by simply thinking about the examples and the exercise behind, you are able to solve. I can say majority of the problems will come. At some problems you will struck. But as per the UPSC standards considered, majority of the problems are nothing but examples taken from the textbooks, the standard textbooks, and the similar kind of problems with regard to the examples, not in detail. Okay. Right. So just take one problem here. So I am giving it as an assignment for the sequence Sn is defined by S1 is equal to root 2, Sn plus 1 is equal to root of 2 into Sn for all n greater than or equal to 1. That's it. And I also mentioned that it converges to the value 2. I have given the answer also for you. It converges to 2. So you just try this problem as an assignment over this mathematical induction technique. Okay. So here I want to conclude my today's session. So tomorrow we will meet. And in the previous class we have done one assignment problem. So I have given the solution. I will post it to the Telegram. You can check. Maybe today or tomorrow morning I will post it. You can check that. The assignment problem. We have reached the solution part, but I got stuck at one point. I have given the clarity in a separate manner for this thing, the assignment problem mentioned. So as and when you have any other queries with regard to the linear programming, you can post queries to me separately. I will clarify the doubts. And mostly I will give the assignment based on the previous year questions for you as a practice. And I request everyone to, whoever solved the problems at first, you post a solution group, so that everyone will have a healthy discussion on the solution part. So as and when the doubt strikes, I am able to there to clarify the doubt. That is my intention, because I believe the discussion clarifies many doubts and gives clarity over the subject, rather than practicing more and more. I hope so. Is that acceptable? In other words, if I have given an assignment, say 1 to 15 problems, you simply do like this, that suppose you have 20 members or 30 members who are ready to solve the assignment. 2 members take one problem. You solve the problem, post the solution group straight away. Others will take care of the other problems, so that everyone will have the solution readily available with them, and they can cross verify that. That is one kind of planning strategy to save the time, having all solutions. Okay. So you can go according to your convenient method. I will give the assignment. So thanks to all. That is for today's session. Tomorrow we will meet on other concepts of this monotone convergence theorem and as well as the sequences chapter.